the presentations, you learn something new even in basic presentations, but the hallway track is just indispensable.
Hello, some time ago, Herb were presenting really cool features, is, as, cppfront and everything. And first thing that come up to my mind was, hey, when I can use all those shiny features, right? That's the first thought. And is, as a general inspection, or as a universal casting thing, right? I want to use that. It doesn't have to be like that. I will be fine with some different syntax, but I wanted a feature, right? And this talk will be like lessons learned talk. I will share with you all my findings, all my failures, all my successes during the way. I already told fellows here in the room that Herb by accident overshared the project, and that gives me opportunity to contribute. He was not probably willing to accept that, but in the end, he did. So, and I'm happy. And I wanted to tell you that some of those features are available now. You can use it. If you have C++ 20 and GCC 10, Clang 12, or Visual Studio, Herb was talking about 19. I don't know how the numbering goes with Microsoft, but this is what you can find in the Compiler Explorer, and I've been using that. Okay, so I'm Filip Sajdak. I'm the head of engineering in CD Auto. I'm helping our teams building HMI for premium cars. I'm also organizer of WROCPP, is a C++ community in my hometown Wrocław in Poland. And this year I turned 40, and I'm currently fulfilling my dream, becoming a speaker of the CppCon. So, and you are now participating in advancing cppfront with modern C++. Okay, so it is all about C++, and Herb probably was saying that a lot already, and that gives me opportunity to introduce you into is operator. So we have an if, which is a variable, and we have operator is, and we have something. And this thing could be anything. So it could be value, it could be type, it could be predicate, it could be template. We can check if it fulfills concept or is it empty, right? So the second thing I have learned during the way is that there is always a paper. I've been seeing fellows that were requesting to Herb, hey, Herb, there's like cool feature, I've invented it. And Herb was just sending the link to the paper. And the paper was usually a couple of years old already, right? So, and for is, there is also a paper, right? So it's a P2392, which describes all those shiny features on the left. On the column in the middle are the features that are currently developed in cppfront. On the white background are the features that are implemented. Like gray one is that is not yet implemented, but probably I will implement it soon. And the lighter gray is are the things that I already implemented, but they are waiting on the pull request. And yeah, and my goal here is to share with you how the development of is and as look like. And what are the pros and cons or any failures during the way. Okay, so X as a type is a type. So we are going to implement multiple overloads of is function, which is a template function that takes, and on the below you see how we are going to use it, right? The type is the type that we are checking, and X is the variable that we are checking, right? And yeah, expected type is here. So C becomes our expected type, and X deduced is usually deduced and is the type that we are checking. Okay, so how we started doing that? So we've created, first function is the function that identity function. So when you ask for the type that you provided as a variable. Is it true, right? So it's obvious. And the second function is the function that have two non-related types at all, right? And it should return false at the beginning. But when you try to compile it, you will see that ambiguity. You heard about, concepts requires, right? So what we have done? Okay, let's put the requires and, block the thing that is making ambiguity. Okay, we add another version, so we are trying to check if C is a base of X, base class of X, right? And we try to compile it, and again, ambiguity. So what we are doing? Yeah, we added another check. And again, you see where is that going, right? So don't do it. Third thing that I've learned during the way is that if you want to learn C++ 20 or 23, contribute to the project that is using it. But please select the project that you find that you are passionate about, because it requires struggle and pain and lots of time, right? But this is the best way you can learn. And this is like the best moment to thank you, Joel Ernesto Guerrero Peña, who is like doing an excellent work reviewing all my changes that I'm providing. And I don't know how he is doing that, but he responded like immediately almost. So thank you, Joel, for all the support. And from that, people, you can learn that you can use concepts for that. And I know concepts at that time, right? But I didn't know one crucial thing, that there is something like subsumption rules. And the subsumption rules gives the real power to the concepts, to be honest. If you tried concepts already and you don't know subsumption rules, you don't try concepts, right? So be aware of that. And subsumption rules are there are a couple of rules. So first is that the concepts can subsume other concepts. What means that subsum concept one other? It means that one concept could include or absorb other concept. I will explain that further later. And the important thing is that it works only with concepts. So don't mix it with the type traits in the requires, because you will just disable subsumption rules. And the tricky part is that the concept are identified by the compiler by their source location. And that's the tricky part. So you can have like two concepts, but created in separate places in your source files, and they will be treated by the compiler as a separate thing, right? And that's the tricky part. Please be aware of that. And when you are using negation or parents in the require clause, you are creating, like, let's say, in-place concept, which have new source location, right? So it won't match to other. Even if the expression will be the same as the other, it won't match. At least compiler won't do that. So it means that subsumption rules won't happen, and you won't have any benefit from that. And I rewrite the previous example like that. It's visible. Comparing to the old thing, you see that there's like less negations, and there's no such method that collects all the negations. They are rather positive ones, so each method says what kind of types it says. And this is like the goal of the subsumption rules. And by the way, if you wanted to learn concepts and all those rules, please use Compiler Explorer. There's like a really cool feature, I don't know if you know it, that highlights the lines of code that are executed. And this is perfect when you are trying to understand which method will match your function call, as it's just highlighted, right? So it's easy. So please, Compiler Explorer will help you learn concepts and those rules, and you will see that sometimes, even if you think that everything is obvious, it's not. And you can just visualize that. So please avoid type traits in the requires. Avoid negations and parents. At least, I'm not saying it won't work, but in cases when it stopped working, please treat it as a point that might be the case. And use Compiler Explorer. Another thing is, whenever you are able to deduce the outcome while checking only types and you are not using the variable, please do yourself a favor and return std false type or std true type. It will work much better when you will try to use those methods or functions inside defining concepts or in any concept or any required clause that is unevaluated. I will show some example. And by the way, when you happen to run some function and fail due to ambiguity, the Compiler Explorer also have some cool feature, which is you can highlight the candidate and it will spot the function that were considered, right? Helps a lot in analysis, what goes wrong. That brings me to the fifth lesson learned. I forget to mention that. I don't know if you noticed, but I have here ambiguity, and there were 3 methods that were considered, and I solve it by providing the 4th method. And what happened? It succeeded. Why is that? So that brings me to the 5th lesson there. So if the compiler has too many options, give him another. Why? Because subsumption rules works that when the compiler have troubles in selecting the proper function or method, it tries to select the most constrained one. And in the situation you've seen, the compilers saw 3 methods that were equally constrained. And I provided the 4th option, which was the most constrained, right? So it selects it. OK, so that concludes the isType thing. So on the C++ side, you can use isType X. And it is pretty similar to isType, but in C++ way. And let's jump into xIsValue, because the previous one was the simple one. So we have 3 options, at least, to do it. So we can treat it as a non-type template parameter and put the value into the template parameter as an auto value, right? So we will somehow reproduce the previous procedure, or create the function that will template function that will take those 2 values as argument to the function, or similar way using auto, but the 3rd and 2nd options are similar, right? And the first option is really cool because you provide to the function information in the compile time, and you can deduce it in compile time, which is always cool. But unfortunately, not all types fit into as a template parameter. It has to be a structural type. And double is not structural type. At least not all compilers are able to deal with it. There are some solutions to that, but if you wanted to find like generic way of handling like generic type, it's not the best way, right? So we end up with the 2nd and 3rd choice. And we will, at first, we develop one method that takes those 2 values. So x is the value that we are checking, and the value is what we are checking against. And what we are doing it here in the requires, we are checking if we can compare those values. And if we can, we just compare it. And if we can't compare it, we just return false, right? And it works. We can provide it, and that works fine. OK, so we deal with xIsValue thing. By the way, those parentheses in the cppfront side are required at the moment. They will be probably removed someday, but at the moment, this is how cppfront parse it. Okay, so let's go to the predicate. So we want to pass as a value a predicate. So we like repeating the same steps. So we are checking in the require clause if we can call the value as a predicate, right? And if we can, well, we just call it, and that's it. And if not, we are repeating the same steps with the value. So it works with the value and with the predicate. By the way, QR code here will bring you to the compiler explorer with exactly the same example. So yeah, if you manage to make a photo, you can jump there. Okay, but there are issues. First, the first requires is more stricter than stud predicate. We require that the value is explicitly castable to bool, which is like hard requirement. And sometimes the predicates are returning something else. The other thing is that when we provide, when we are checking the double, like 42 free, and with the lambda that is taking int, it returns true. Right? Do you see something weird here? Yeah, it appears that implicit casting takes place, right? So 32.free is cast to the int, so we lost the comma free, and it's equal 42. And unfortunately, it doesn't work with generic lambdas. And with the free function, at least those generic ones. Okay, so let's deal with it one by one. So X as a predicate. So I told you that the stud predicate has completely different requirements about the return time, and it expects Boolean testable concept as a return type. Do you see the minus between Boolean and testable? Is it allowed name? No, because Boolean testable is not the real concept. It's an exposition-only concept. So it's not required by the standard. It presents how it could be implemented. So you can find the implementation, and I just implemented by the rules, and I provided here. So now value has to return the Boolean testable thing, and if it does, I'm running it. Okay, the second issue with the implicit casting of argument is the harder one. So what we need to do here is that we need to somehow recognize what argument is the function or lambda expects, right? And we need to try implicit cast of x to this type. So I've created the type trace argument of that it's taking the type of the value and provides the argument type. And now it works, right? That still returns, so first one works correctly, but generic lambda still doesn't work. What happened? So it appears that when you have generic lambda, you can deduce the type, right? Because there is no type. It is generic. You can put there anything. So what you can do is you can check if you can create the value with the dexval. And the dexval, I don't know, how many of you used dexval in the past? Yeah, so it's like mimic creating of the value, right? So it's not doing it for real, but in the unevaluated context, it's treated as a value. And if you can create it, it means that the argument is known, so you can proceed further and you can check if the cast is correct. And if you cannot create it, it means that this is a generic function or generic lambda, and everything, anything you can do is just to run that, because you cannot deduce anything if it's completely generic. Okay, and this is how the argument of is implemented. Some details. The magic happens in two places. So first, dexval here is evaluated or to function pointer, and it goes to the upper one, Or it could be lambda, so if it's lambda, it matches here. And what it does, it just takes the address of call operator, and it calls the helper again. And when it doing that, it goes or here or here. Despite of the trace, it will end up with the return arc. And we are just checking the return type with the CPP2 type of, which in fact is doing decal type together with removing qualifiers and reference. And that's it, and that's how we get argument off. And this is the whole thing. And tell me, do you like it? Is it readable for you? Yeah. So I must confess that when I developed it for the first time, I put everywhere comments, because it is not obvious what happens where. And we can do better than that. First of all, I've created concepts that replace those nasty requires. But it didn't help much. You see the CPP2 type of things all around. So you can give work for the compiler and explicitly say, hey, that does it for me, and voila, it's doing that. And one side note about writing concepts, because I've created here a couple of them, right? So I created as well the inherited from thing. And the most important part is the order of the template arguments. So you have to remember that concept can be used in few places. And for example, you can put it as a type name into template parameter list or before auto on the function argument list, right? And how it's working is working like that the F here will become the first argument of the inherited from concept, and the T will become second one, and the same will go here, so the auto, type of the auto, will become the first argument of the inherited from, and the T will be the second. And this really can help you. And I will back to that in a moment. So what we can do better is we can split this big function into smaller ones using concept subsumption rules. So one big function can be split into a couple of smaller functions which might become more readable. So first one is the function on the top is the function where the two types are unrelated. So again, we return false. The second one is the type. The type restriction is when the predicate like returns true. So predicate like thing will return true when the V is a predicate that is able to consume X. And that make us split it to the second function. And the third function is the function that when two types are comparable, it will be just like that, right? So I split it to the three functions, but it's not yet finished. So each const X function we can treat it as a next split point. So I've created again thing. So and here will be something not obvious, but bear with me for a second. First function is the predicate like thing, so it stays. We just call the value with it. So and you must remember that we are talking in the space of restrictions. So this is the only restriction that we provided. That there is a predicate. Second one is a tricky one. So there is a predicate like, so we provide the predicate, and there is a defined argument, and we are returning false. Why is that? And it's just because the third one is even more restricted, because it has predicate, it has defined argument, and the argument is convertible to X is convertible to the argument of the function, right? And it then calls the function. So it's not obvious, And okay, when we will change the order of the arguments, like here are the v is the first and x is the second, we can change the order of that, and then we can like put those predicates into the type names, which can make it more readable or at least more condensed. And this is how it looks like. To be honest, you have to use to it. To be honest, because I've spent a lot of time with it, and thanks to Compiler Explorer, I try to understand what is the reasoning behind that, and it's not always obvious. So the six lessons learned is when writing a concept, put tested type first. It allows you to use this concept in multiple places, and it will be aligned with the standard concepts. And speaking of standard concepts, the predicate light thing appeared to be exactly a stud predicate, so I replaced it. And the last predicate, value comparable, I call it, is exactly the same as stud equality comparable with concept, so I just replace it, right? And the last issue that we have is the free function that is generic. So it seems that it ends up with providing a function that expects the function pointer that is taking x. X is the type which is deduced from the argument you are providing. And we are expecting exactly that kind of function pointer, right? And the cool thing is, or maybe not, is that compiler will implicitly cast generic function into that type. So it will like force the generic function to take x as an argument, right? And it will match here. And when we have it, when we have a match, we just call this predicate, and that makes it working. So that solves an issue with the predicates. And we have a question about emptiness. So herp provides a using which defines empty as a void. And how can you ask for a void? So you are following the same pattern. So you are asking is void, and you are providing the argument. And if you expect the function to take some explicit type, you can use same as and provide the type, and exactly that type will match this this function, right? And the second one have another requirement. So first one here has a pointer-like thing. So if x is a pointer, it could be shared pointer, or it could be unique pointer, whatever. It behaves like a pointer. It will match here. Here we have like second one is a null pointer type, and the stud monostate is a third. To be honest, third one and second one, I don't know if herp will accept it, but I propose it. Is that clear? Okay. Yeah, there's a question, so go ahead. So the next thing is x is a template thing. So to match that, we are using the old template parameter, right? And when we would, for example, ask, here you have an example, if v is a stud vector, does c become a vector? We are trying to deduce what kind of template parameter is using, so it matches here. And if the v match that argument here, it means that we are dealing with a vector, right? So we are returning true type. And this is like good example of things that we are not using this variable at all. We just concentrate on types, so we are returning true type. And when there is no match, we have another function which like takes anything, right? So we still provide the vector here, but we are using like some generic unrelated type to catch it, and the stud list match it as it's not, as v is a vector here. And now the cool stuff. Yeah, go ahead with question.
Yeah, I was just curious for his template.
That's a perfect question. I won't show it here, but I provide additional overload for a signature as stud array have. So type and size. But yeah, good question. Thank you. And then now the cool stuff. I've been thinking a lot how to pass a concept to the function. So we have a variable with some type, and we have a concept. And how do you pass it to the function? Any ideas? If you come up with the idea, you will ruin me because I've been thinking on that a long time. Okay. I'm glad that you did not. So, okay, I will show you. So, you can use a lambda. And you have two options here. Lambda is like cool stuff, right? And the coolness of lambda is that you are defining it in the place where you created it, right? And so you can pass the requirement inside the lambda. And what I'm using here is I'm putting the concept on the explicit template parameter list of the lambda, C++20 feature, right? Cool stuff. But you have another option. You can put it as an requirement for the argument with auto. But it will collide with the predicate thing, which we already use. So I selected that one. And how do you check it? So it's easy. That is how you check it. So I will explain it. So I provided an overlay, like the function in the middle. I provided an overload of a function that have one requirement for the type of v is that is callable with explicit type of x. And above, you see what the requires is doing. So I'm creating the value which is of v type in the requires. Here it behaves like decval if you don't know the syntax. So I have a value with the type of v, and I'm calling the template operator, like template calling operator with explicit type of x, right? And what is happening here? So when I'm calling it on the lambda with floating point, it means that this call operator requires here a floating point type. And I provided here a double, right? So x become a double. It goes here, it goes here. If it match, it means that it match concept. And the entire requires become true. And you have a match. And if you provide like stud integral, the double doesn't fulfill the requirements for the stud integral, and you have a false. Easy? So we come to the 7th lesson learned. If you struggle, try lambda. And to be honest, I've never seen as much using of the lambda as in the cppfront. So lots of cppfront features are implemented using lambdas. Usually immediately called lambdas. So really, if you are struggling with something, try lambda. Okay, so we end with the concept. We have others here, but I won't get into the details because, to be honest, they are pretty the same as the thing with the values. And if you follow my recommendation and you provide the functions that are returning stud true type or stud false type, it will be piece of cake. Easy said than done. But we have some special types that cppfront treats them specially. We have variant, any, and optional. Why I say that they are like special? Because we can check if they are empty. We can check if they contain a type. So not if they are a type, if contain an int. And we can check if they contain a value that we are asking for. And this is and probably couple of more. And when I joined cppfront, I saw something like that. So there was like is function, which was checking if type T is currently in the variant. So, and I saw like, then it was like 10, and later on Herb created it to the 20. Hard-coded checks. And here is like the check that is checking emptiness of it. I will get back to it. You don't have to read it. This is the most important one. This line repeats all the time. So what it's doing, to be honest, so CPP2 type of is just checking what type name is on the index n of the variant. And if it's evaluated, we are checking against the type that we are asking for. And if there is match, we are checking on the variant itself if the index of the currently set value is equal to what we are checking now. If they are the same, we are returning true because the variant contains the value, the type that we are asking for. As easy as that. So we have here and variant type, and we have variant type index. And let's do some tutorial here. So let's implement the time find if. So really cool thing that shows how you can use C++20 feature, which is the lambda with explicit type list. Here I'm creating I'm using stud, to create a stud index, right? So it works like that when I'm providing time when I'm asking for time find if int long double index sequence create for all those types index 0, 1, 2, and I can ask about the number of those indexes on the ES with the size of ... and I receive the number of types, which is 3. Let's create some level of indirection because I want that find if it will take the kind of lambda which will be doing the magic. So I'm providing here a lambda, and the lambda is called with exactly the same number, so it returns 3. So let's go further. Let's do the folding expression with the comma operator, and let's expand it. So each fun will be called with each index. So that's why we have 0, 1, 2. Like all the indexes are called, right? Let's go further. So as you notice on the beginning, we need the index of the type to be available in the compile time. And we cannot pass it like through the argument of the lambda because it won't stay the const exp thing. So we are going to pass it as a template argument to the call operator. So we are like moving I to the template parameter in the lambda, and so that we need to call it in this way. It doesn't change the behavior, right? The only thing is that it's available in the compile time. So let's add the type that is provided here. So now I'm also writing the name of that. So integer long double and with the indexes. We wanted to stop when we find the type, so I've simulated it by checking if the index is 1, and it should stop. So the OR operator is doing exactly that. So it will stop when the lambda will return true. So we are stopping here. So let's get further. It will be nice that the type find if return the index of the type that it found. So we are doing here a magic. So I'm creating a variable in the type find if. I'm passing it a reference in the capture list, right? So, and here is the magic. So whenever operator, call operator returns true, it's evaluate that. And if that's evaluated, it saves the index. Here's a comma and true. And that means that this whole expression will end with true. And that will break the further expansion of the OR with the folding, right? And we are returning the index. And now we can compare it to something. And just to have some user-friendly thing, I'm using stud variant and pos, which is exactly -1. And we can check against it to know if we find it or not. Easy? I hope so. Because we now will be using that for the is and later for the s on the variant. Okay, so what's happening here? So here in the middle, you see exactly the same line that I've shown you in the beginning. We don't have to deduce the type because we already know the type because we are traversing the types. So we know that what the X is. We know what type we ask for, and we know index of this type. So we are just comparing it explicitly. And here is something that we need to pass, right? And additional checking of the emptiness, we can move to the separate function as we are using the concept subsumption rules, and here we create an overload for that. And unfortunately, I don't know if you noticed, but in upper right corner, I'm providing information on which compiler it's running. Unfortunately, the previous one was requiring Clang 13, and that one required Clang 14, and Herb expects to have it running on Clang 12. And I must confess that usually those issues end up with the internal compiler error, right? So, but there is a solution. You can create some intermediate type that's have type in it, have some inline static const index in it. You can pass it as a function argument, as a value, and you can explicitly deduce it with the lambda and use it directly here as a type and a value available in the compile time, right? And it works on Clang 12. So yeah. And what we do is we replace the left hand side with the right hand side here. And additionally, we provide the is with variant with possibility to check unlimited number of types in variant, not fixed one, it's 20. So takeaways from is. I believe we can implement is operator as a set of overloaded functions. A compiler explorer helps. Please check it if you are struggling. Concepts are really powerful, but you have to learn them. And please visit Compiler Explorer to learn them. And if something is not working expected, Compiler Explorer, and try to keep the function signatures similar. I found some cases, I don't understand why yet. I have plenty of functions that were taking cost reference, and I provided one function with a perfect forwarding, and it creates ambiguity, or something, something was wrong. And I started to replace all the const ref to the perfect forwarding thing, and it helps in some cases, but not at all. But I did not finish that. But please be aware that it might cause you some trouble when you did that. I didn't finish the porting to all functions to the perfect forwarding. I cannot tell you if it will work or not. Lambdas can serve you, in most of challenging issues. Let's go to the S operator. So again, you have an it's a variable, you have an operator, and you have a type. And that's it. We are not using S for something else than type. And what we are expecting is that we are going to or bound. So for example, if we have some related types like polymorphic types, or there's kind of any kind of relation, right? We expect T to become L value reference or R value reference or const reference, or whatever, that we can call later. We expect that there will be safe cast. So for example, assigned that 8-bit integers can be safely cast to the 16-bit integers, right? So this is safe cast. There are potentially unsafe casts. So the cast that might be a loss, so unsafe, right? And what we can do here, we can provide runtime checks for that. And for cases that we don't know what to do, we can just return non such. And we are going to the with the same pattern. So for the negative case, we just return non such, and you see it works. And we have a discussion with Herb that, hey, let's let's make an error as soon as possible. Static assert looks like a good solution. And yeah, it works. So when it fails, it triggers static assert, and when it works, right? But there is an issue. You might have a need to check in the requires if your AskCast is correct. And if it's correct, you want to use it. But unfortunately, if you are having static assert in AskCast, you end up with static assert. So require clause is treating static assert as a static assert. It's not a requires failure. And okay, so we are like going back to the non-such again, but we can do something else. So as we know that in the failed casting, we are returning non-such, we can check if in the requires, if the AskCast is returning non-such, and if it does, we know that the casting failed. And if it doesn't return that, we know it's a success, so we can use it. And if you wanted to have this static cast thing, you can do it. And you have here an example how it works. And this is how it is really implemented in the cppfront. So we provide like another level of interaction, right? So cppfront generates the code, right? So whenever it sees AskCast, it creates as underscore, which does the same thing as fun we're doing. So it's checking if the as is non-successful, and if it does, it just is doing static assertion, and if it's successful, it's just run the as, right? And why we are doing that? Because as cppfront is generating this code, it can generate completely different code in normal cases and in cases when the as is used in the requires, right? So it saves us from running static assertion inside requires, and it works, right? So when I call as with underscore, it triggers static assert, and as without it, it returns non-such. So that brings me to the 8 lessons learned, which is static assert is not kind for a require expression. It's not. So you need to remember that if you are going to use those functions in the requires, you need to take special care of that. And okay, so let's continue. So identity function. So we are providing like a variable with the x, and it happens that the x is exactly the same what we are asking for, so we are just returning it. But as you can see, we have like 2 of those functions, one with const, one with non-const reference. And I will leave it as is. There is a possibility to use perfect forwarding, but I will probably skip it. If you are interested how it's doing, we can talk after the talk. So it works like it should. So it's still working with the ends. Like non-such is also returned when there's no match. Well, with the strings, when we are passing and asking for string, we are getting just reference to a string. If the string is const, we are getting reference to const string, right? So everything as expected. With literals, we are passing literals as non-type template parameter here, just to be able to deduce it in the compile time. And we are using the predicate castable, which in fact, it works like it's checking if the explicit braces initialization can be done on that. If it's possible, we are running the static cast on that. And this could be intriguing for you. So this is a special case for the types like stud optional, for example, or stud variant or something like that. So something that like have the value type and can contain it and can be created from the literal that we provided. And we can check it how it works. So when we are providing, even long to ints, it works. We can initialize double with int as well. If we provide minus to the signed integer, it works, but for unsigned, it's non-acceptable, right? So it works. If we cannot do explicit casting, we need to do a special care. So we are doing runtime checks. So if happened that both types are integral, and there is no possibility to convert it with the explicit braces operator casting, we are running that. So we are casting this value, and we are checking if we lost information during the way. And if we did, we just run assert, and if not, we just return the value. And probably this is maximum what we can do in those cases. And variants as a T. So you already know the type find if thing. So we are running again the lambda init. What we are doing here, we are doing a small trick here, but we are checking if we found the type that we are looking for. So and if we found it, we capture the pointer of it to the PTR. And the PTR happens to be exactly the type that we are expecting because we are asked that. It's outside of the lambda, and we capture it by reference, right? And if we manage to find it, we just return true, which stops the expansion of the type find if. And if there is no match in type or index, we just return false. And in the end of the loop here, we are checking if the pointer is null. If it is, we just throw the exception. And if it's not null, we just return it. And again, we are returning deck type here just to provide the better type deduction. And as you can see here, I'm using here what? Is it perfect forwarding? Our value reference, exactly. That to be a perfect forwarding, we cannot explicitly say about the variant. It should be X or whatever, right, to use the perfect forwarding. So we need to provide the overloads for non-const reference and const reference as well. And it changed as well the constants of the pointer. And it worked, as you can see here. The example is also provided on the compile explorer. We can provide perfect forwarding thing. This concept is checking if the type here fulfill is a stud variant. So it's checking if it's a template stud variant. This pass the constants of X to the T type and find if receive an X, because now X is an X. Right? And the only thing which we know is the stud variant, but we don't know what the type list is, right? And we just pass it to the overload of the type find if, which is deducing the list of types, and proceed like forward to the previous version. So it worked. And this specification of template, specialization of template concept, which I used before, is a perfect example of why you should return a true type. So we are just checking if it is with the template here is matching the X. If it is, it should return true type, and we can match it without evaluating anything else except of the signature of the function, right? And that's why I tell you, give yourself a favor. And yeah, and constants it looks like that. So just is a conditional T, but please remember it's using isConst value. But please remember that if X is a reference or is a pointer, even if it's const, isConst v will not return you information that it's const. You need to remove reference and remove pointer. So that's what I'm doing here. We can get more into details later. So another thing is we are checking the polymorphic types. So the thing is, when you have two polymorphic types, you cannot say anything about them. They could be completely unrelated to each other, but they can, spot exactly the same object, because your object could inherit both of them. And that's it. So whenever you have two polymorphic types, the only thing you can do is you can just use dynamic cast and pray for the good. Of course, we can do perfect forwarding here, but I won't get too much into that. We can discuss later. And pointer-like thing. I added here it just because I want to show you if you will go with good concepts and subsumption rules, you can add additional function without the trouble. And that was something I've discussed with Herb on the conference. So I asked about his paper, and he told me, this overload is for pointer-like things. And I already had the concept pointer-like, so I just added. And the cool stuff is when I receive pointer-like thing, I'm asking for the type name C. So if the C is the same type which pointer points to, and I'm able to check if it's not null, I'm just dereferencing it, and that's it. And what is the good thing here is that I don't have to make any other changes in any other function, right? The subsumption rules took jump here and solved all those ambiguities for me, right? So that's perfect. It's like open-close principle in action. Okay, so as takeaways, it is possible to introduce like a common way of casting in C++20. Static assert is not kind for requires. If you follow the good rules, you can add new overloads without touching old ones, and that's perfect. And Lambda explicit template argument list is excellent. So again, don't forget about Lambda. Perfect forwarding may save you from writing multiple versions of the same function, but it has some tricks that you need to not forget. And please remember that it might collide with some other functions overloads. And last thing, I will only mention about it because, okay, so what is a unified function called syntax UFCS? So it's a thing that when you are, here I'm using the normal POSIX fopen, so I got the file handler. Here I'm calling on this normal file handler fprintf, normal printf, with this argument, and normal fclose. And what the cppfront is doing, it's wrapping those things in the macros, really cool macros I will show you in a moment. And the macro is doing like cool thing, it's checking if my file is an object with fprintf method, or maybe there is a free function that takes it as a first argument. And that's how it works. And this is how it looks. So this is like variadic macro that generates variadic lambda. Herb put the comment there of and that is just the beginning. So this is the version I saw when I joined. And now this is the previous version, and this is now the actual one. So I decided not to go into the details because it probably deserves like the separate talk. One thing that I wanted to tell you. During the way we added force inline to this generated lambda, we try to use no discard. I will get to that. There are some workarounds for bugs in compiler. We handle templates with multiple template parameters, and we provided UFCS chaining. And yeah, and I wanted to tell you about takeaways from that. So first, lambdas always help, right? Another lambda here. Macros are really powerful, but you don't want to write or use them, right? And we're laughing that I was saying that I don't want my kid see me doing, right? When I was like writing these lambdas inside those macros. Commas are always tricky, right? Inside the macros, but there are solutions for that. There are variadic macros. That was like in innovation. It's not served by all compilers. But if you wanted to search for it, look for the VA opt. C++23 lambdas will have attributes U, and that will help us support no discard, which is currently not supported by all the compilers. And currently this macro, like all other things, I can recommend you that you can write it by hand and use in your code. And this one, no, please don't do it. It's meant to be generated, and that's it. And unless you want to generate it, then go for it. And 9th lesson learned, and I'm finishing. Preparing presentation will help you find better ways of doing things. I must tell you, I rewrite almost like all implementation of is and as while I've been working on that. So, like, really. And it ended up with pull request. You have QR code if you wanted to jump there. To be honest, there is like what I've shown you today. It's there, and there is like lots more. So if you will find some time to go there, review it, and provide me a feedback, I will be more than welcome. And let's learn from each other, guys, because that's a pretty awesome way to learn new standards. Thank you. And we have 5 seconds for questions. Can I have a questions or not? Yeah, okay.
Take like 2 minutes, yeah.
Ah, cool. Any questions?
So
Yeah?
I have one. Okay, so first of all, I think it's really cool to get an insight on kind of how the sausage is made over there. That's
Cool.
both terrifying and
Yeah, it is.
One specific thing. So the biotube effectively have special handling for variants and for a few other types. That was kind of the part that's kind of rubbed me the wrong way, just kind of philosophically speaking. Like the idea is to kind of have everything should be composable. You have your type has certain attributes, then you should just kind of fold into that. Maybe I want to implement my own variant or something like that. Mm-hmm. Kind of what's the mindset around that? What are your thoughts?
So mindset is that there is custom is and as operator. So you can provide one for your own type, and it will be used. I think that's it. Unless I did not understand the question.
Yeah, no, that was kind of the gist of it. So, but I guess the point is like if you provide things like cast operators, mm-hmm. It's kind of the standard C++ operators and things. Mm-hmm. Shouldn't those things kind of automatically fold into your implementation? You still kind of have to implement the is and the as.
No. The thing is, I didn't show that, but in those is and as, there is a check if the type provides its own operator or not.
Okay.
It's not well supported yet, like entirely, but that's the direction.
Cool. Okay. Cool. Thank you.
Yeah. Thank you.
So I have a question about the universal function call syntax.
Yeah.
And I remember there was a previous note that Herb put down about like choices between methods, class methods having precedence over. 2 questions on that. Number one is that still the way things are going to go? I think that note might have been a little bit old, not sure. And the other thing is, how did you make that precedence happen in the macro? That might be another talk, but I'm just curious.
So the whole magic is that there's like context ifs that is checking the requires. So as far as I remember, first we are checking if this is a method inside the object, and later on, like the else if is a free function. So that's how it does.
And is that the policy that's going forward? Is that like?
I don't know, to be honest.
Okay.
I don't know. That I don't know.
Thank you.
Thank you.
Hi, it was a very interesting talk. Thanks for giving it. One thing that I just wanted to mention, because I just recently came across this trick myself, the issue that you were having where you needed to pass a constexpr like index into the function, and if you pass it as an argument, it loses the constexpr status. One thing that you can do to try to decrease the noise, because like that template operator angle bracket is kind of unfortunate. If you pass it as an integral constant, like an instance of integral constant, I just came across that recently. But
to be honest, I developed it in like lately. So to be honest, I've been developing the whole thing during the conference, to be honest, because I've been finding so many bugs and things that, I've been like pushing that forward. So I've developed some of that I've shown you today, like in last days. So sorry for any mistakes in the code. But if you find anything that I did wrong, I love to hear that, because, this is like completely experiment for me. And I'm using the opportunity to learn, C++ 20 and 23, especially those hard to learn features. So if you have any feedback, I'll be happy to get it. Thank you. Okay, I think that's concluded. Thank you, guys.